Hi folks, welcome to a video about the number e. This goes with section 8.3 in your textbook. And after this lesson, we should be able to use the number e as the base of at least two different exponential functions. And we're also going to use the natural base e at least twice in real life situations. We're going to see one with exponential growth, and we'll see an example with exponential decay in real life situations. The number e is really important in different areas, science like physics, biology, chemistry, and in finance too. Actually, we'll see a problem with finance in a second here. So what is the number e? Well, this is a formal definition, but I want you to look over here on the right side. E is about 2.72. You do not need to memorize that. We're not going to see it all that much like we did with pi. We know pi is about 3.14. But e is about 2.72, and this decimal does keep going on and on. But if you know it's over 1, that's really the important part here. E is irrational, just like the number pi is irrational. We can't write it as a fraction. So we just say the number e, just like we say pi. Okay, so what is the number e? Well, I'm looking at this part of it right here. We've seen something like this before, right? In our compounding interest problems, where we had a equals p times 1 plus r over n to the mt, right? We've seen this kind of look to it. It's just a little simplified, isn't it, right? The rate is gone, and we just put a 1 up here, and we got rid of the t, okay? For some reason, right? You guys don't need to know why, but that's what we did. Well, when we do that, and we compound this more and more and more often, like faster than every millisecond, we get that base really just goes to a particular number, and that number is what we call e. It happens so often, and it happens in the natural world, that we call e the natural base. So again, we're going to see this a lot in natural events, and some that are not so natural, like banking. Okay, so first thing we want to do is just get kind of comfortable with playing around with e, and we're going to treat it like the variable in a way when we simplify, even though it's really a number. So something like letter a over here, where I have e cubed times e to the fourth, well, I'm multiplying with the same base. I'm just going to add those exponents. That's really it, just like we did with variables. In b, that's how quickly I'm doing a. I'm done with a. With b, again, a little simplifying. Well, I have this 10 over 5. Okay, that's 2. And now we have division with the number e. Well, this is really subtracting with our exponents, right? So I can say e to the negative 4 minus 2, or e to the negative 6. Or if you don't like that, you can say it's 2 divided by e to the positive 6. Either one is fine, right? We should be comfortable with both of these by now. But again, that's just a little playing around with the number e and with exponents. So these two are a little amped up, but you guys try these. Okay, so what happens here? Well, the 4 gets squared, and the e to the negative 5x gets squared, which I have a power to a power here, right? So I'm just going to multiply those exponents. And I get 16e to the negative 10x. Likewise in d, I'm going to break this apart. I'm going to do this one piece at a time. Well, I'm going to do the 4th root of 16 is 2. And then I'm going to have the 4th root of e to the 12x. Well, this is the same as e to the 12x over 4. Well, that's e to the 3x. Not so bad. Again, same properties with exponents that we had before, just a different looking piece. Okay. So, yeah, we're going to play with the calculator a second now. So, if you don't have a calculator, go pause it and bring this back, because you need to find this on your calculator. We need to find the button for e on your calculator. So where is it? Well, let's see. Here's my calculator. You can kind of look along with this one here. You kind of get away with this one here. But the number e, there's actually 2 spots for it. The one I'm most concerned with, oops, and it went away. There it goes. I'm going to have to just kind of, I guess, point to it on, can I do this? No, it's not really showing up on mine. Look on the lower left. See this button down here that I'm poking away at? So right above that, on my calculator, it's blue. It says e to the x. So if I push, notice how it's in blue, which means I need to hit my second button, and then my natural log, excuse me. Hold on one second. Okay, so fix my issues. So again, I hit this button that says seconds, and then I hit this button down here that says LN. See that button that says LN right there? I'm gonna clear mine off here. But that makes the blue button work, right? So now I have e to the, and then I could just put in my 3 and hit enter, and this is going to do e cubed for me, and now I get about 20.086. Let's call it. Okay. So that's e cubed, and that's really all you need to be able to do with calculators. Just find that button and use it properly, right? So you go ahead and try e to the negative 0.08. So again, seconds, and I'm going to hit that button that says ln and negative 0.08. Hit enter, and again about 2.72 to the negative 0.08. I can try it that way. About 2.72. to the negative 0.08. And again, mine's rounded, so it's not going to be exact, but it's pretty darn close, right? So again, just a little verification that we have E correctly, actually. Some of you folks may have noticed that over here on the right side, see the division button? See how right above it is the number E? It's not a letter, it's the number E. You can also use that. It's not nearly as useful because it's not, you don't have the exponent already there for you, right? I can plug it in, but then I would have to do to the third. And it works. It works just fine. It's just not as nice and quick. Okay, let's move on. So remember, E is just a number. It's about 2.72. So here's the important part about that. If we were to graph an exponential function that has base E, it's going to graph just like it did when we had base 2, because they're both greater than 1. So we're going to see exponential what? Growth or decay, folks? We're going to see exponential growth. Okay. So let's take a look at a graph. So I'm going to graph f of x equals e to the x plus 2 and then minus 3. So here's what I'm going to do. I'm going to ignore the fact that there's any kind of transformations going on here. I'm just going to graph the e to the x. Well, exponential growth, in fact, all exponential functions go through this point 0, 1. And I put the 1 up here in my function so that you can see my initial condition up there. Because it's not really shown, but you need to know that there's a 1 there. So it goes through that point, and then I know that it looks kind of like that, right? I might be off by a little bit there, but that's certainly, I have the asymptote right, and that's definitely the look of it. Okay, so what happens with our function? Well, because of this plus 2 inside the exponent, that's going to shift it what way? Well, it's inside the exponent, it's horizontal, it's the opposite of what it looks like. So this is going to go left 2. So this point here, I'm going to grab the point itself, maybe. The point itself goes left 2, and then I'm going to bring the whole function along with it. Okay, what happens next? Well, because of this minus 3, it's outside the exponent, it's vertical, it's as you see it. So everything's going to go down 3. So I'm going to grab my point and go down 1, 2, 3. I'm going to bring my function along with it. And that's approximately what my graph should look like. Notice here how the horizontal asymptote is now shifted down 3. The shifting left to right didn't affect the asymptote, but it just shifted down 3. Okay, so what's our domain and what's our range? Well, our domain is everything we're allowed to put into the function. So if I'm looking at the graph, look at it this way. What x values get used? Well, it's all of these, right? All these x values get used, even all the way out here, right? So my domain is all real numbers. Every x value is allowed to be put into the function. So I'm going to write it nice and fancy like that. The question is, and this one's a little tougher to see, what's the range? Well, the range shows all the y values that get used. Well, if I look at my function here, notice how down here there's no y values, right? There's no y values down here. As I work up, what's the first y value that we come across? Well, it's almost negative 3. Negative 3 actually doesn't get reached because of this horizontal asymptote, but it's just greater than negative 3, right? So my range is going to be everything greater than negative 3. And again, we can see that by this vertical shift, right? If we knew what the range was before, that y could be greater than 0, then it all just shifted down 3. So there's our new range. Okay, so let's look at 2 application problems. We'll do one at a time. So let's say we deposit $1,000 into a bank account. Again, we're going to get an astronomical 12% interest and 12% annual interest compounded continuously. Here's a key word for you. Write that in your notes. If you see the word continuously, in fact, I haven't told you the rest of this part yet. So if you see the word continuously, this is going to tell us base E. And we're going to use this formula that I'm about to show you here. Okay. So you don't need to know all the backstory. You don't need to know all the details of this. But our compounded growth formula for banking that we had before, this becomes A equals PE to the RT. So does that look like a word that you've seen before? Have you seen this word PERT before? There's actually a shampoo called PERT. But anyways, it makes a nice little word, so it's easy to remember. Hopefully easy to remember. Okay, so let's go ahead and use this. So what's the balance after? Well, I'd say just 1 year. Okay, I probably could have made that a little more difficult for us, but I chose 1 year. Okay, so let's see. So our balance A is going to be, well, we're putting in $1,000. E is just a number, right? And our rate is 0.12 times 1 year. And I'm going to go to the calculator for this, and I'm going to see what answer it gives us. So I have 1,000. Again, I need that number E, so I'm going to do second, and then this LN button. We're going to see what that LN means in the next section, actually. And then this is to the 0.12 times 1, which I really don't need to do, so I'll just hit enter. And I get just over $1,100, $1,127.50, I'll call it. Anyways, it's actually a little nicer using the number E, right, than using this this compounded growth formula, right? That's a little compounded interest formula. That's a little trickier to use. The PERT formula, the continuously compounded. Remember I said this word continuously. If you see that word, it's PERT. It's base E. Okay, let's move on here to another function. This is going to be a little physics application here for you. If that worries you a little bit, don't worry about it. I'm giving you guys the formula here, right? You guys don't need to memorize these formulas. These are things I'll give you guys. Okay, so the atmospheric pressure, which we're going to call capital P, by the way, that's in pounds per square inch. On an object, not of an object. That should be on an object. D miles above sea level can be modeled by this function here. P equals 14.7 E to the negative 0.21 times D. And D, again, is in miles above sea level. Okay. So what's the air pressure at sea level? Well, if you're at sea level, you're 0 miles above it, right? So we want to know the pressure when D is 0. 14.7 times e to the negative 0.21 times 0, right? Okay. So another way of looking at this is, what's our initial value here, right? If we put in 0, what's the initial value? Well, this whole term, we're going to get e to the 0. What's anything to the 0? Well, it's 1, right? So our initial pressure, or pressure at sea level, is going to be 14.7. And the units here are pounds per square inch. So right now, everywhere on your body, about the size of a quarter, that's about a square inch, there's 14.7 pounds of air pressure from way, way miles up pushing down on your body. Little neat fact there for you. Okay, so let's go on to the second question here. How much pressure would you feel on the summit of Mount Everest, which is 29,028 feet above sea level? So first thing of note here, the units that we have, D is in miles, right? D is in miles. Okay, and I give you 29,000 feet above sea level. So that wasn't too nice of me. So first thing we need to do is convert that, right? We need this number here, this 29,000 feet. We need that in miles. Okay, so here's what I'm going to do. I'm going to take my 29,028 feet, and I know I want to end up in miles. So I'm going to do what we call dimensional analysis. I know I'm going to multiply by some conversion factor. I want to introduce miles. I'm going to make a little fraction here. I want to introduce miles in the numerator, and I want to cancel out this feet. So I need feet down below. So when I do that, now I need to know the conversion between miles and feet here. Well, I know it's 1 mile for 5,280 feet. Again, you don't need to memorize that. that's something I'll give you, or more likely I'll probably just give you the altitude in miles to make it a little bit nicer for you. But anyways, just want to show you a little conversion here, and this ends up being about 5.5 miles. It's like 5.4977. I put a whole bunch of decimals there because I want to be precise. So in order to be precise, I need to carry these decimals all the way. Okay, so I'm going to go ahead and just put this into my function. So my pressure is going to be the 14.7 times e to the negative 0.21 times that answer of 5.4977. So I'm going to let you guys put that in your calculator. I'm going to go ahead and do it right now and give you guys an answer here. Okay, so I did as I said I was going to do. Here comes the pressure at, what do we say, about 5.497 miles up. Is about 4.63, I get about 4, again, pounds per square inch. So not a whole lot of pressure up there. So your lungs are going to feel it when you're up there. Yeah, so there's not a whole lot of air. That's about a third of the air that we have at sea level. Okay, one more question for you. This is a little surprise question. So at what altitude would the air pressure be 10 pounds per square inch? So we're kind of working backwards here a little bit, right? Here's our function. I'm just going to rewrite this again because it's way up on my screen. 14.7 e to the negative 0.21 times the distance in miles above sea level. So I want to know at what height the pressure will be 10 pounds per square inch. So I'm going to put 10 over here for the pressure equals 14.7 e to the negative 0.21 d. Okay, so there's a little bit of a problem here, isn't there? If you want to think about unwrapping this, well, I can divide by this 14.7. I can do that. But we don't know yet how to unwrap this e to the negative 0.21 d, right? We don't know how to unwrap exponentiation, at least not for all cases, right? So this is actually going to be a focus of the next couple of units. So I'm going to finish up this problem on the calculator, but at the same time, I'm going to let you know that we're going to see this in the days to come here on how to solve this problem here. So all I'm going to do here is I'm going to put one of these, the left side in y1, I'm going to put the right side in y2, and I'm going to find the intersection, right? So I'm going to go ahead and find the intersection. So that's something that we've done many times before. I'm going to leave that to you guys as an exercise, but here comes the answer. So I get a distance here above sea level of approximately 1.835 miles. So hopefully that's what you got too on your calculator. But again, graph the two functions, get a good window, find where they intersect, and hopefully you came up with about 1.835 miles as well. Okay, so did we do the things that I said we were going to do? Did we use the number e as the base of at least two exponential functions? Yes, go back in your notes if you want to and take a look at that. We did that. Did we see the base e, the natural base e, in at least two real-life situations? Well, we saw the banking problem, we saw PERT, right? And we saw the air pressure problem, right? So we saw in two cases there. Hopefully this was useful for you folks and that you gained a little bit of knowledge from this, and I look forward to seeing you guys next time in class.